To really understand the when, where, and why of the late heavy bombardment, you must go back in time, around 38 million years after the Big Bang. In fact, when the universe started to shape itself into what we know and can see today. When the Big Bang happened, the universe was created in less than 3 minutes. At this point, however, the universe was much too hot and violent for atoms to exist. There was only energy. Not until 38 million years later did the universe slow down enough for energy to transform into subatomic particles, which is the first matter to be created. The very first elements were created in the core of a star in a process called stellar nucleosynthesis, where chemical elements can assemble, the first of which were hydrogen, helium, and lithium. The death of a star is the creation of the period 4, 5, 6, and 7 elements in a process called supernova nucleosynthesis. Here we have a protoplanetary disk, which is a disk of dense gas that surrounds a new star. This will turn into a solar nebula that will evolve into a planetary system. What was once a star surrounded by dust and gas is now a star with orbiting planetoids, resembling a solar system. However, these young planetoids have not yet been set into their orbital paths because of collisions still taking place within the system. According to the giant impact hypothesis, during this time a planetoid named Theia collided with the Earth, resulting in the Moon's creation. Theia's mantle and a significant portion of the Earth's silicate mantle were thrust into space. The leftover materials from Theia mixed with the materials from Earth, and this eventually led to the formation of the Moon. Life on Earth had finally been given the chance to grow and evolve, and it was. Unfortunately, the late heavy bombardment had yet to happen. Although much of the matter had been enveloped into the planetoids up to this point, there were still many smaller bodies left over, not considered large enough to be deemed planetoids. These comet-like bodies ended up in a large ring called the Kuiper Belt. It is thought that a gravitational surge caused by the orbital interaction of Jupiter and Saturn sent Neptune careening into the ring of comets in the outer solar system. The disrupted comets were sent in all directions and collided with the planets. These water-rich objects may have provided much of the water in the Earth's oceans. Today, much of the evidence of a late heavy bombardment is hidden under billions of years of erosion and shifting plate tectonics. But there is much more apparent evidence that we can see almost every night in the sky. It is easy to identify the massive amounts of impact craters on the moon's surface, indicating a similar situation for our Earth. Although it might seem that the late heavy bombardment, which is commonly referred to as the lunar cataclysm, had a very negative implication on our planet. But the opposite is quite true. It has been surmised that many of our precious metals arrived on the Earth's surface through these impacts, materials like silver, gold, and platinum. Earth's original supply of these elements had sunk into its molten iron core as the planet cooled. Thanks to the new supply of rare metals, we are now able to mine for them today. Much of our technology heavily relies on these delivered metals, as they play a huge role in wiring, circuit boards, the ability to resist rust, or endure extreme temperatures. Perhaps the greatest threat to humanity now is the possibility of an impact similar to those in the lunar cataclysm. Around 26 to 30 million years or so, a mass extinction occurs. One theory is that every 30 million years, the Earth is subject to heavy bombardment by asteroids or comets. Most scientists have agreed the dinosaurs became extinct around 65 million years ago from a major impact, not volcanoes or climate issues. This is a red flag for us today, considering we are definitely past due. On its way to the impact, the asteroid pushes aside the air in front of it, creating a hole in the atmosphere. The atmosphere above the impact site is removed for several seconds. Before the surrounding air can rush back in to fill the gap, material from the impact escapes through the hole and follows a ballistic flight back down. If the asteroid hits the ocean, the surrounding water returning over the hot crater floor is vaporized, sending more water vapor into the air, as well as causing huge steam explosions that will greatly compound the effect of the initial impact explosion. A large enough impact will break through to the hot lithosphere and maybe the even hotter asthenosphere. Large impacts can blast thousands of cubic kilometers of vaporized material and planet sediments into the atmosphere, expanding into space and enveloping the entire planet. These high-energy, vapor-rich materials re-enter the atmosphere and heat up air temperatures to the point that the Earth's surface is consumed by fire. In the year 2028, the asteroid 1997 XF11 will come extremely close to Earth. If it does hit Earth, what you will have is a mile-wide asteroid striking the planet's surface at about 30,000 miles per hour. An asteroid that big, traveling at that speed, has an energy roughly equal to a 1 million megaton bomb. It is very likely that an asteroid like this would wipe out most of the life on the planet. To try and understand 1 million megatons, we will use a small-scale reference. Let's say that an asteroid the size of a house crashed on Earth at 30,000 miles per hour. It would have an amount of energy roughly equal to the bomb that fell on Hiroshima, perhaps 20 kilotons. An asteroid like this would flatten reinforced concrete buildings up to half a mile from ground zero. Needless to say, we live in a very fragile state of existence on many fronts. If we don't get hit in the year 2028, perhaps we will in the years to come, reverting our planet back to how it was in the late heavy bombardment. It won't be the first time it happened.